I'd like to explain a little bit about the piezoelectric effect, which allows us to do ultrasound tool, but also to then talk about more practical elements about how to set up the machine itself. There are three main physics things that I would like to concentrate on today. The principles of wavelength and frequency, about acoustic impedance, and then finally about anisotropy. And I think if you understand these three principles, ultrasound becomes significantly easier. So how can we do ultrasound at all? Well, it's because of the natural phenomenon that occurs, which is the piezoelectric effect. And the piezoelectric effect is essentially materials that when you pass a mechanical stress through them, they vibrate. And when you apply alternating current, then the disc that you provide of that material will expand and contract with the same frequency as the current. And it then produce waves, and those waves are determined what we call the wavelength. And the frequency at which compression is past a fixed point is the same as the frequency of vibrations that the transducer vibrates with and the voltage applied. So that's the principle of what happens in ultrasound. So what does the probe look like? Well, this is the basic probe design that you'll have in virtually every ultrasound machine. It's essentially a disc at which is the dark blue bit of the probe is actually, the darkest blue bit is actually the piezoelectric disc. And typically it's produced from a material which is lead, zirconate, titanate, so most crystals are made from this. And this is the expensive stuff. This is what makes the probe cost between £4,000 and £7,000 depending on which probe you get. But that's the expensive part of the probe. And that's what will shatter if you drop it on the floor. So don't drop your probes on the floor. The lighter blue, just in front of the piezoelectric disc, is the plastic plate. And we're going to talk about why you need to have that, and we'll talk about that in a minute, once we've talked about the physics. And likewise, the slightly darker blue behind the very dark blue bit, where the arrow is. Oh, sorry, here's the, thank you for that. So this is the plastic disc, the matching plate, we'll talk about that. This is the piezoelectric disc. And then this darker blue stuff here is the epoxy resin. Again, the reason why it's there will become clear in a moment. And then this is where the wire is, which applies the current to the piezoelectric disc and allows you to produce the sound waves at all. And then it's all housed within a plastic casing, which essentially ensures that all the sound waves are concentrated within the probe and aren't lost to the air around. So here's some just very basic principles. I don't want to spend too long on this slide, but essentially, axial resolution is your ability to distinguish between two structures at different lengths that are parallel to the beam. And it's determined by it's related to the spatial pulse length. And the spatial pulse length is determined by the wavelength. And the wavelength is determined by the frequency of the transducer. We'll go through all of this in a moment, and it will become a bit clearer what all this stuff means. So here's the basic principle. So your frequency is the frequency of the probe that you have. So when you go to any machine, you'll be able to look on the side of the probe and it will tell you what the frequency of that probe is. So you'll get these curly shaped ones. They tend to be slightly low frequency probes. You will see that they tend to come in two frequencies. Ones which are very low frequency, which will be in the region of about 3 to 8 megahertz. They are more for abdominal scanning, so that doesn't really relate to you, so abdominal gynae scanning. You can get slightly higher frequency curvilinear, which are around about 10 megahertz. That's more for a pediatric population, or if you need curvilinear, you need slightly more resolution. We'll talk about that later. But the ones that are relevant to you most are the linear probes, and they're the ones that are, as the name suggests, they are linear probe, and they're the ones that you need to become familiar with. And they will come in a variety of frequencies. They can vary from being around about 9 to 10 megahertz when you're doing vascular scanning, to doing around about 12 to 13 megahertz, and then you can get very high frequency, which are these days between 15 and 18, and then you can get ultra high frequencies, which are 24 megahertz, which comes with the newer matrix probes that the newer manufacturers are producing. We'll talk about the usefulness of that. But essentially, the key thing about all this is that your sound waves are produced in parallel lines, and the maximum resolution that you will have will be in the period when the sound waves are parallel to one another. Beyond a certain point, the sound waves start to diverge, and at this point, the information that you receive from this point on the far zone distorts your image. So if you're looking for something and you want to know the detail of something, you want want to have a look at it where your sound waves are still parallel. By the time it gets to this point here, the sound waves are divergent, and so the resolution of what you're looking at will become worse. So this is a very important thing. It's a bit like having the focus of your camera. This is where your maximum resolution of your photograph will be. If you're trying to photograph something really far away and you haven't focused your image, you'll get a blurry image. Sort of like that. It's not quite the same, but that's the basic principle. I'll stop here for 1 second to tell you that the reason why the curvilinear probes, which are lower frequency, are curved is because the image in a curvilinear probe is produced by the divergent sound wave. It has a very, very short near zone. And so it's produced. The reason why you have a curvilinear probe for abdominal imaging is because you need depth, because you're looking at structures that are quite deep down inside the abdomen. So you want a divergent beam for those structures. But for musculoskeletal imaging, and the imaging that you will be doing in rheumatology, the curvilinear probe, you don't want to have a divergent beam because it doesn't give you very good resolution. It's very good for depth, but you won't be scanning anything beyond 2 to 3, 4 centimeters below the skin depth, unlike what you need when you're doing abdominal imaging or gynae imaging, for example. So, what's important here? The important thing here is that the near zone, which is the bit where you have the best image, is inversely proportional to the wavelength. So, high frequency probes and your frequency is inversely related to the wavelength. So, a high frequency probe will produce short wavelengths, and short wavelengths will allow you to have a larger near zone. And that's what we want, really. We want to have a nice, good near zone. So the higher frequency probe you have, the better resolution you will have, because most of your image will be coming from the near zone. The downside is with short wavelengths, the penetration through the tissue is very great. And therefore, if you use the high frequency probe for a deep structure, the sound waves just don't make it because they're too short. So the key thing is to find the right probe for the right job. We'll go through that in a minute. Oh, the other thing to say, yes, this is the next one. The next thing to say is that you are able to, on the probe, to focus your sound waves. So if you're looking for a structure at a particular focal zone, you can actually concentrate your sound waves to that particular structure, so you don't have to maintain that parallel system. So if you're looking, if you're looking for a structure that's around about this level, you can alter on the machine the focal depth, and you can ensure that the focal zone, rather than being this broad area, is really concentrated to a much smaller area, so it can give you much better detail of a small structure that's a little bit deeper in your structure, but also you can focus the sound wave. So, here's principle number 2. Now this is where it gets a little bit heavy, but just bear with me in a second. The acoustic impedance is really the key thing that determines how your image will appear, and that is essentially the acoustic impedance of the material is independent of the frequency of the probe. So this has got nothing to do with the frequency of the probe. This is just an independent issue, and that issue is that the acoustic impedance is how the sound wave moves through particular tissues, and that's determined by 2 things: the velocity and the density of the structure. And that is determined. The velocity is determined by elasticity, which is the square root of elasticity over density. Now these are fixed numbers. So sound waves from tissue move at a rate of 1,540 meters per second, and through bone move at 4,080 meters per second. These are fixed numbers. So this is something you need to appreciate. And what determines how much of your sound wave comes back is a differential in the acoustic impedance. So it's not just the acoustic impedance of the structure, but it's the acoustic impedance of 2 adjacent structures, which determines how much sound wave is returned. So, we'll talk about that in a minute, it might get a little bit heavy. If you look at the differential between bone and soft tissue, you determine that 30% of the sound waves at that interface, so if you've got bone at depth and then you've got soft tissue just above it, 30% of the sound waves will reflect back to your probe, so that's what we'll get back. Okay? Now, why is that important? It's important for a number of things. It will determine what you're able to see in your image, but actually, even at a more basic level, it determines how you set your probe up. If you were to apply the piezoelectric disc, do you remember that disc that vibrates when you put a current through it, or expands and contracts and produces sound waves? If you were to apply that disc directly onto the skin, then you would have an issue. Because the differential coefficient between the disc and soft tissue is 80%. That means only 20% of the sound wave will reflect. So you just wouldn't get enough information. So what we do is we actually apply a plastic plate right on top of the disc. Do you remember I talked about that plastic plate on top of the disc? The reason why we apply that is because the reflection coefficient between plastic and soft tissue is 10%. So this means that actually having a matching plate in between the piezoelectric disc and the soft tissue increases the transmission of sound. And that's why we have that. By contrast, the reason why we have the epoxy resin is because the epoxy resin ensures that the sound waves go directly from the piezoelectric disc and transmit through that epoxy resin. Now, we can improve our sound wave transmission even more, and we have to really, because the differential between gas and soft tissue is 99%. So if you apply the disc, the plastic plate directly onto the skin, you will have a layer of gas between the plate and the skin. And that's a problem, because the reflection coefficient there is 99.9% if you've got gas in between the skin and the plate. So what we do is we apply a coupling agent to eliminate the gas. And that's actually all the gel does. And actually you don't need to use gel, you can use water, you can use saliva. In some cases, if you're draining an abscess, you can even use the abscess fluid. I mean, you shouldn't, but this is, the point being is that the only purpose that the gel serves is to eliminate the gas between the plastic plate and the skin. And that's why it's important to have that, because by doing so, it allows a greater degree of sound penetration or sound transmission. That's it, that's the main physics bit. There will be one bit afterwards, but if you can grab what I just explained to you, that will allow you to manipulate your machine. So I'm not going to spend too much time on this, but the basic ultrasound setup is as so. This is my registrar, who's now my consultant colleague, 1 week before I joined, before I came here. That he, at that time, had to listen to what I did, and so I made him sit up with me. But most machines look very similar. They will have a panel that looks something like this, but the key button, they'll have lots of buttons. It looks like the cockpit of an aeroplane. You don't need to know about every single button, but the basic things that you do need to know about is that there'll be a freeze button somewhere, there'll be something that allows you to save image. Often there'll be P1, 2, 3, 4. 2 is often to save a video clip. 3 is it allows you to put a photograph. 4 has some other function, it doesn't really matter. But the main one will be something that saves the image, something that freezes the image, something that acts like a cursor on a mouse, that's the select button. You'll have a roller ball again like a mouse. And then the other buttons that you'll need to know about, really out of all of these, I don't want to confuse you too much, look for power Doppler. Don't worry about colour Doppler, that's only if you're doing vascular imaging, which I will talk to you about later on. But for the purposes of general musculoskeletal imaging, it's power Doppler is the thing that you'll need to know about. Oh, there we go. And these days you'll have a touch screen set up. Again, most of these, there will be lots and lots of different things that you can adjust, but for now, let's keep it simple, let's concentrate on these things. During the practical sessions, there are things that you want to talk about, anything in particular, I'm happy to talk about those things, but I won't do it right now. This is the key thing I think to ultrasound, and actually this is the thing that most of my trainees I actually have to adjust their grip, because they have been doing ultrasound for 3 years by the time they come to me, and they want to do musculoskeletal imaging, and they just don't hold the probe correctly. In musculoskeletal imaging, I would advise you to hold the probe really close to the tip. That's my technique anyway. The reason I do that is because it ensures that you have quite tactile feedback when you're holding the probe. When people hold the probe back over here, you just don't understand which angle the probe is in. And in musculoskeletal imaging, it's so important to know where you are on the body without having to look at your hand each time. Having a probe right against the tip of your fingers means that you will always have tactile feedback as to where you are with the patient. Now this is something I've created, which is a tool that I used myself when I was training. I then have started teaching it really, and this is something called what I call the image optimization cycle. And it's a cycle that you can use to continually improve your image. It's just this very simple paradigm that one can use to ensure that the imaging is always good. And we're going to visit each one of these things. So when you start by scanning, make sure you choose, choose the right probe. So as I said to you earlier, there are curvilinear probes that often have some sort of a code and will give you some hint as to where the frequencies of this probe are. So this probe will be 1 to 7 megahertz, this will be 3 to 12 megahertz. So every manufacturer has slight variations, but on the probe itself, often will have some sort of code that will let you know what frequency. The higher frequency probe will have higher numbers, 18 and 16 megahertz. This is called what we call the hockey stick probe. We'll talk about the usefulness of that during the practical session. I tend not to use it these days. I don't think it's the best probe, but nonetheless, it is something that can be available. And now I'm just going to show you the differences that each of these things can have. Now, it might be a bit difficult because the light, if the lights can go off just at the front. Is it possible to have the lights up there? If it is, that would be great. But essentially what I wanted to show you is that the difference between the two probes when you change the frequency. And the thing that I like to focus in on is the cortical surface of this proximal phalanx. If you see the fuzzy border here, when you just change the probe to the 18 megahertz, you haven't changed anything else, the focal zone, everything else is similar, you'll see that the cortex is just as crisper on that, proximal phalanx will be crisper than by only changing the frequency. That's really the only thing that will change here. So the first thing is make sure you have the right probe. The next thing is make sure you have the right preset. Now, most of the manufacturers will come with their own presets. They will have them predetermined. But I would urge you that when you get the new machine, if you are buying one, then bring your manufacturers back. Bring your application specialists in with you so that they can adjust the image, because every machine requires some calibration. It's often not a plug-in way. But you can adjust it. So I have my own presets here, and these are my other consultant colleagues. They all have their own presets of what they prefer. You can see that if you put on a thyroid preset, if you look at the fuzziness of that cartilage, of that proximal phalanx, and then you look at how crisp this is, you'll see that nothing else is changing. The focal zone is the same, everything else is the same. All we've done is just change the preset, and you can see how much crisper your image becomes by choosing the right preset if you've adjusted it appropriately. The next thing is having good contact. Remember, we talked about eliminating the gas. Make sure you've got good contact. This is a really good technique that you'll see in musculoskeletal imaging. If you've got something that you're looking at that's very close to the tip of the probe, very close to the skin surface, for example, skin lesion, so you might do that when you're looking for sarcomatous lesions. So I've seen quite a few either sarcomatous or sarcoid lesions. In the last year, I've seen 2 cases of cutaneous sarcoid, and those are very superficial lesions, and you do need to apply a gel gap so you can actually see the lesion. Otherwise, the sound will just penetrate right through it and go to the structures that are deeper. But having a gel gap can be a really clever technique, allowing you to see things a bit more superficial. So we're on contact. We'll now go on to gain. Now, gain is a way of improving your image. You'll see it will be a button that often has 2D written on it or something along that line. And actually, it's just a twist of a button, but you can see that changing the gain, you can see everything else is the same. The preset is the same, the depth is the same, all we've adjusted is the gain. I won't go into the physics of gain, it's really quite boring, but the point being is that it just improves your image resolution by just adjusting the gain appropriately. The next thing is the depth. So you can see that in these 2 images, the only thing that's changed is the depth. If you have an image that here, all of this area is completely wasted information. The machine is trying desperately for the sound waves to get through the bone and try and give you information from down here. But actually, it can't give you information from down here because the sound waves aren't getting through the bone. So you're actually just wasting the computing power and your probe ability by having your image like this. Actually, if you just adjust your depth, you can get a much better resolution because the machine is then concentrating the near zone resolution and giving you a much better image. Adjusting the focal zone makes a big difference as well. So you can see these 2 images. I'm not sure how well that's projecting, but you can see that the only thing that will change is just ensuring that, do you remember when we talked about the beam that's diverging to improve your resolution? But at the moment, the machine is trying to look for a structure that's down here somewhere. But actually just adjusting it and moving it up will allow you to have a much better resolution image in your near zone. So making sure that the depth is appropriate and that the focus is appropriate. And then finally, we come to anisotropy. If you've done all of these things, you've got the right probe, the right preset, the contact is good, you've adjusted the gain appropriately, your depth is good, your focus is good. If you're still getting an ugly image, then it might be because you're doing something called anisotropy. Now, in musculoskeletal imaging and with linear probes, this is a real problem. When you're imaging something that's parallel, the sound waves should be going down the probe and then reflecting back 90 degrees back to your probe again. If you are imaging a structure that's at angles, so that might be because of a vessel or a bone or a finger, then some of the sound waves that are sent out are reflected but not caught by the beam. And what the machine interprets that as is that this must be a structure that doesn't reflect sound. And therefore, or it transmits the whole sound, so it fills in the gap with black. So it thinks that there's no sound waves coming back from this thing. All the sound waves are being transmitted right the way through the structure, like for example, it's the lung or the gap, bow or whatever. And so you end up getting an image that looks dark and patchy. So actually the only adjustment that one needs to do, what would anyone have to do to adjust to improve this? Anyone from the audience, tell me what do you have to do if you have a situation with anisotropy? What does the person have to do? What does the sonographer have to do? Anyone?
rotate or twist?
Yeah, absolutely. All you have to do is just change the angle of the probe so it's parallel to the structure. That's actually all it takes. It's just a change. And there's another reason for holding the probe right near the tip, because you can just make a very slight adjustment. And it's not huge, it's not a massive change in wrist position. It's a very slight change in wrist position, and all of a sudden you parallel with this structure and the image improves. This is the difference that anisotropy has. If you have your probe at an angle, you can see that you can't see any of the tendons. You can interpret this as tendon rupture, you can interpret this as tendinopathy. But actually all we did was just adjust the probe angle, and you can see that the tendons are now invisible. They are visible, they are not torn, there's no tendinopathy there. The final thing, I won't talk too much about Doppler effect, but I think you'll be speaking more about that in your lecture, so I'll leave that for now. But essentially, if at the end of that whole process, you still have an ugly image, it still doesn't look right, change your probe. Change your probe and go to one level down. So if you're starting on the 18 megahertz, go down to the 12, and start this whole process all again. Make sure your preset is correct, make sure your contact is good, gain, depth, focus, anisotropy. Image is still bad, change the probe again. Now, on the newer probes, you can actually adjust the frequency, so you don't have to necessarily go down. So on an 18 megahertz, it will have 3 settings. It'll have when the probe is operating at very high frequency, so around about 18, but you can turn it right the way down to about 12. So actually, you might not necessarily need to change the probe, but the principle is the same. Change the frequency of the probe, okay? And then go through this process again. And that's why this is a cycle. It just goes round and round and round. So you might end up with some very large patients using the curvilinear probe, because it's the only thing that allows you to look at that structure, because nothing else works. And if it still doesn't work, then it's stuff. You have to think of something else, a new different modality. So that's everything I had to say. Sorry that it was a bit heavy for the morning, but I hope you found that useful. If you have any questions about anything that I've said, please do find me during the practical session.